Welcome back to another video. In previous video, we understood binary representation of B+Tree nodes, and also we understood how indexes are represented on disk. For that, we went over topics like data alignment, order of nodes, tracking the root node, and problems with storing and parsing 0 in a byte array. In this video, we will see more code examples, and we also meet more challenges and solutions. Before we continue, please note that I am recording these videos while I am implementing this database. So there will be mistakes, there will be many changes, and depending on the time you watch these videos, you may not find the exact codes in the repository. The first interface you want to look at is Index Storage Manager. It is used for actions like writing, reading, updating, and removing a node from an index file. As mentioned in previous video, an index file can store indexes for different tables. So if we assume each table has an integer identifier, most of these methods require this integer identifier in order to know which file or part of the file to modify. Again, each node is represented as a byte array, and this is true both for cases that a node is an input or when it is an output. The node data object, which is part of many of the outputs, also includes byte array and a pointer, which means, for example, when we write a new node, we can know what has been written on the disk and the location it has been written to. Also note that most of these methods return completable future, which means these operations are non-blocking. However, most of their current usages are in blocking way. We also have two methods that don't modify the data on disk. Close method closes all of the file handlers opened by an implementation of this index storage manager. And getEmptyNode returns a byte array, which is in size of a B+Tree node. The first implementation of index storage manager is base file index storage manager. It is an abstract class, so we cannot construct it from outside without implementing the abstract methods. And the constructor accepts 5 properties. The first property is path, which is the path to the directory where this index file is stored. Second one is header manager. We will take a look at this interface shortly, but we have discussed what a header is in previous video. Using header manager, we can get header of this database, and using a header, we can understand where is each index stored and find the root node of the B+Tree. Next, we have engine config, which right now is not complete. The engine config has some parameters, such as the degree of the tree, how many nodes will be allocated each time we are growing the tree, how long can we wait to acquire index files, and maximum size of a B+Tree index file. Back to our base file index storage manager. The next constructor parameter is file handler pool, and we will discuss this shortly. And last parameter, in short, is size of a B+Tree node, which we discussed its importance in previous video in data alignment section. So let's see the purpose of this file handler pool. The interface looks like this. We can request a file channel by providing a path, timeout, and time unit. We can release a file channel and also close all of the open file channels. But to understand the real purpose, we need to head back to our Blackboard. So imagine we have multiple index files and a single file index storage manager. It would be a fair question to ask what happens when multiple threads want to read from a single file. Normally, for each of these threads, we would open a file, which means for a single file, we could have multiple open operations. Also, after we read the information we want from a file, we have to close the file. So we would also have multiple close operations. Opening and closing a file multiple times per each thread is not really performance friendly. That's why we need a solution to reduce these open and close calls, handles requests from multiple threads, and keeps a file open as long as it's needed. Fortunately, Java has asynchronous file handler class, and we can use it for thread-safe file I/O operations. So that one is done, but completing the other two tasks is our job. And that is the purpose of a file handler pool. Basically, when we ask for a file from file handler pool, it will start with checking a storage, and this pool is basically a map of paths to file handler. If the requested path by index storage manager already exists in the pool, it will be returned from the pool. Otherwise, first a new file handler would be created, which is of type asynchronous file handler. It will be added to the pool, and then it will be returned. The index storage manager should not close the file handler, and that is because it doesn't know if other threads are using this file or not. So to solve this problem, instead of only storing file handler in this pool, we store a wrapper class which not only stores file handler, but has another element called usage count. Basically, each time a file is requested by index storage managers, this usage count increases, and whenever they are done with it, this usage count decreases. As a result, for example, whenever a thread calls close method on index storage manager, then the file handler pool should also be cleared, which means all of the files should close, and we won't close files until their usage count is 0. Now, there is one more complicated issue left. First, we need to know why did we assume we may have multiple files? Or in other words, why can we have multiple files? Let's say we have an index file, and our goal is to store multiple indexes from different tables in the same file. Now, going back to our discussion in previous video, each time we added a new node, it was added at the end of that file. This assumption worked fine when we had a single index file for each table, but if we want to add multiple nodes of different indexes into a single file, we would have a problem. So let's say for our first index, we have 4 nodes, which are shown in blocks of white color. And the question would be, what happens if we want to add a node to the next index, which we show in green? So we could add the new node at the end of the file, despite which B+Tree it belongs to. But as a result, we will have to implement a database level lock each time we want to modify this file. That's because when asynchronous file channel wants to write to a file, it requires position and a byte buffer or byte array. In order to write to the end of the file, which is here, this position basically equals to the size of the file. Considering the fact that multiple threads may be working with multiple index storage managers, a race condition will be created between different threads, which all want to add a new node at the end of this file. As a result, the last thread would win the race, and it will overwrite the data written by previous threads. Therefore, using a lock, we can prevent this race condition. And this isn't really the worst solution, but it is also not the most performant one. Because we should consider that we have multiple tables, and each table has at least one index. Before we move on to other solutions, I want to also mention that there is a more organized way to achieve this goal. It doesn't satisfy the need for a database level lock. It actually even has a little bit of additional problems, but it has an advantage of separating where each index nodes are stored in a single file. So the idea is basic. Whenever we want to add a new node, which is not of the last index in the file, we will start by finding the first node in the next index, which is here. Then we push all of the contents in the file from that position to create a space for the new node. And then we add our node in the allocated space. And for obvious reasons, this allocation method itself is not performance friendly, and it is the additional problem that I was talking about. Also, we should track and update where does each index node start in this single file. Currently, I call the class that looks like this, compact file index manager. And the class that uses this strategy, I call it single file index manager. And there is a third implementation of a storage manager, which creates multiple index files. And each file represents a single B+Tree. And I call this implementation extended file index manager. Also, generally, I have allowed the developer to chunk the files by setting a maximum index file size in engine config. So these two implementations are what we can call chunkable. So I think now we can answer this question. We may have multiple index files if A, extended file index manager is used, and B, the implementation which is used is chunkable. Now, whether a chunkable implementation is beneficial or not is a question that each developer should answer for themselves. But the benefits of using extended file index manager is that instead of database level locks, we can use table level or index level locks. But the difference between index level lock and database level lock is that in index level lock, we only lock the index file which is being modified. But in case of single file index manager, whenever we want to write into any of the indexes, we have to lock the whole file, and all of the indexes would be locked. Let's go back to the file handler pool. We understood that this pool reuses an open file handler, but since the number of files are unknown to us, and they might grow as we use database more and more, then in some cases, we might face another issue which is called too many open files. In most operating systems and Linux, there is a limit of how many files a single process can open. And the concept of files does not necessarily mean old plain files like the ones that we are writing to right now. It can also mean sockets, pipes, and other things. So there is a way to change the amount of this limitation in your Linux system. However, we may also want to be able to limit the number of open files and sockets in our program. Therefore, the file handler pool has two implementations. One is unlimited file handler pool, and the other is limited file handler pool. Obviously, in second one, we can set the maximum number of open files. So let's go back to the code. We talked about what this index storage manager interface is, and right now there are few classes implementing it. The main one is base file index storage manager, and it's an abstract class. And the idea is that most of these file index manager implementations work the same way, but the main difference in them is how they generate the index file path and how do they allocate a space for new node. As you can see, both of these methods are abstract. We will take a look at the contents of this class soon, but as you can see, it has three implementations and we have talked about each one of them individually. We have already seen this base file index storage manager and the constructor. We now understand what a file handler pool is. So now let's take a look at other methods. First, we have this abstract get index file path, which depending on the implementation, It returns different paths based on table and chunk. Then we have this protected acquire file channel, which reads an asynchronous file channel from the pool and also increases the usage count. Of course, when we are done with working with the file, we have to release it, which will reduce the usage count. To get the root of a table, we first read the header. And if in the header we don't have a root, then we complete our completable feature with empty optional. Otherwise, we first acquire a file channel and we go to the position of the root node and start reading as large as a single node size. When that is complete, we release the file channel. If there was an error, we complete exceptionally. If we couldn't read a valid node, we will complete again with optional empty. Otherwise, we create a new node data, which has the pointer to the location of the root node and the byte array of the root node data. Returning an empty node is very straightforward. Reading a node using position and chunk is also like reading the root node. And to write a new node, we need to know the table, the byte array of the data, and whether it is a root node or not. We first grab the header and try to allocate a space for new node in the file. And that itself, as I mentioned, is an abstract method which is implemented differently per each implementation. And it will return a pointer to a location where we should start writing to the disk. If the node data doesn't have a padding, here we will add it. And in the end, we again acquire the file channel, write the data to the offset, and when this is complete, we release the file channel and complete our completable feature with the node data, which includes pointer to the location where we write the data, and the final byte array, which may include the padding. Also, if the node was root, we will update the root node in the header file. The rest of the functions are pretty straightforward. Updating a node has very similar behavior to writing a node. And for now, removing a node means that we store an empty byte array in the location of the node. And to see if a table exists, we just check if the file of the table exists. Moving on to file handler pool implementations. This is the unlimited file handler pool implementation. It has a concurrent hash map of file handlers, where the key is a string, which is the path, and asynchronous file channel wrapper, which, as I mentioned before, has a reference to file channel and usage count. When a file channel is requested, it will be created and added to the map if it is absent. The usage is then incremented, and then the file channel is returned. When a file channel is released, we just have to get it from the pool and decrease the usage. And also to close all of the channels, we loop over items in the pool and close each one of them. Whether or not this commented code was a good idea is a discussion we will have later. But moving on to limited file handler pool, most things are the same. We still have a concurrent hash map, but we also have a semaphore. This semaphore controls how many files are opened at the same time. So this time when we want to acquire a file channel, we will wait till the semaphore has an empty space. And each time we release a file channel, we release the semaphore as well.